There we go. Okay, so let's start off with a quick announcement. I sent out an email this morning. I made some adjustments to the first assignment, which is due on Friday evening to be submitted via CrowdMark by 11:59 p.m. So it's due end of day on Friday. The adjustments were the removal of question 8, which was a hypothesis, which gave a null and alternative hypothesis and essentially just asked what is wrong with this statement. So that question got taken off. And questions 9, B, and C were also removed, which were another hypothesis test and a comparison between the results of that test and the confidence interval in 9A. So the updated assignment sheet is on Blackboard, so you can download the updated sheet. The CrowdMark page has been adjusted to accommodate for the change. However, I could not delete the last question. So on CrowdMark, it just kind of says ignore this in the very last box, which, means ignore it. Right, so those are the adjustments that have been made. The hypothesis testing stuff will be on the next assignment, and we'll probably start that by the end of the week, I hope. I think. And it just seems it's a little bit less, stressful to do it this way than to have that stuff on there and potentially only get to it on Friday. All right, so let's pick up where we left off last class. So as a refresher, the main discussion that we had on Friday was regarding the distribution of a random variable. And in particular, what we had focused on was describing the distribution of the sample mean. Now, we went through some discussion about why we can consider the sample mean to be normally distributed. And the result of that discussion was basically the sample mean is a function of a set of random variables. So therefore, it too must be random. Now, the fact that it is a random variable essentially means that we can find a distribution for the sample mean. And this will be very important to us when we start talking about confidence interval construction and hypothesis testing in the second lecture set and for the next month or so, or next few weeks or so. All right, so we looked at an illustration of the first situation last class. The first situation is the easiest one to deal with. So if the population from which we are sampling is normally distributed, then X bar, the sample mean, will also be normally distributed. So the distribution of X bar follows from the distribution of the data that we are working with. So if X is normal, which is the data, then X bar is normal, which is the sample mean. Now, visually, the effect of increasing sample size is that the sample mean becomes a more precise estimate. So the 4 histograms that are shown on slide 18 are meant to represent this idea. So in the first histogram, you have the distribution of the population. And then in the second, third, and fourth histogram, you have the distribution of X bar as sample size goes up. And you can see that as the sample size increases, the peak of the distribution goes up and the tails come in. And this represents, in some sense, convergence to the mean. So this is representing a tighter distribution, which means that we are getting more precise estimates for the population mean. Okay, now if we can assume normality of a population, then we can assume normality for the values in the samples that we will collect. And that's going to give us the ability to conduct inference, as we will see in lecture set 2. But it also gives us the ability to make meaningful statements about, for example, the sampling error. And on slide 19, we just have a simple illustration of how we can make a statement about the sampling error. This illustration draws on the techniques that we had developed in 151 when we learned how to use the standard normal table. This isn't something that we're going to focus on very much, but the point of this exercise is to first just kind of remind you of the kind of techniques that we are going to be using in this course, and Second, to show you that normality is a powerful assumption. And if we can assume normality, it again gives us the ability to make very meaningful statements and in many cases to conduct inference using standard sets of hypothesis tests and confidence intervals. All right, now the last part of this lecture set deals with, the central limit theorem. Okay, so on slide 21, this slide does not relate to the CLT. This is again just kind of an aside. So every once in a while in Stat 252, I like to throw in these little extras. They're not meant to confuse or stress anyone out. The point of these is just to give you a little bit more insight into how things can change in different situations. In the context of the examples that we will focus on in this course are usually going to involve what are called infinite populations. So where you have the ability to sample repeatedly without any kind of constraint. In practice, this isn't always a realistic assumption. Most often we sample from finite populations. So populations that are of a defined size. So you do not have an infinite number of samples. When that is the case, we make adjustments to our estimates. So the equation on slide 21 here, which shows the standard deviation I can't spell. Deviation of sample mean. Okay, this is the adjusted standard deviation of the sample mean to account for finite population size. So again, just a little bit of an extra that in different situations, we make different compensations depending on what we are working with. Okay, now the main the next big topic from lecture set 1 is how to handle non-normally distributed populations. So there will be many situations where we want to work with a data set where the population is not normal. So how do we do this? Well, it turns out that as long as we collect enough information from that population, regardless of whether it is normal or non-normal, well, as long as we collect enough information from a non-normal population, we can assume that the sample mean is normal. And this is what the central limit theorem tells us. So from a visual perspective, if we consider a distribution that is left skewed, like we had on slide 22, if we collect samples of varying size from that distribution and then construct means for each of those samples and then plot the means, we can show that those distributions return to normality as sample size increases. So for example, on slide 24, we start off with a population or the sampling or the distribution for the population. Okay, so this is the density curve for the population. Okay, and then this part here is mu. So you can see that the peak here, so this would be the peak is to the right of mu. So we have left skewness. So this would be what we would classify as a non-normal shape, right? It's not that symmetric bell curve style shape that we are accustomed to. Okay, so what is the effect of taking samples of increasing size from this non-normal distribution? Well, here we start off with the sampling distribution when n equals 2. Okay, actually I should say sampling distribution of x bar. Okay, so you can see that you still have mu here. The peak is still over here, but this is now very slightly left skewed. Okay, so the skewness in some sense is disappearing. And the peak of the curve is starting to get closer to the middle, which would represent the center being pulled closer to the mean, I should say. So the peak is starting to get closer to the mean, right? Now, in the third example, we have the sampling distribution of X bar when n equals 5. All right, now you can see here we have mu, and then here we have the peak. Now these are almost sitting right on top of each other. Actually, we can see that that black and that red line are basically sitting right next to each other, or very, very close to being equal. I mean, it really does look like they're equal when you look at the plot. So now what we have is a sampling distribution that is symmetric. So we started off with a left skew, and slowly as we increase sample size, the sampling distribution of X bar became more and more symmetric. And then finally, we have the sampling distribution when n is equal to 10, and we can see here the same phenomenon. So this is a symmetric distribution. So the point is, if you start off with a population that is non-normal, as long as you collect samples that are big enough, you will have a sampling distribution for the mean that is normal. Now, it's very important that we are able to distinguish between the distribution of the population and the distribution of the sample mean. It's very common that students confuse these ideas, and they will say things like, I collected 30 observations, so my sample is now normal. That is not the case. If you collect enough information, the distribution of the sample mean, so the sampling distribution of X bar, becomes normal. The sample itself will always have the same distribution as the population. If you collect information from a left skewed population, you should have a left skewed representation in the sample. But if you continually sample over and over and over again, so you collect multiple samples, and for every single sample, you build a sample mean, and then you construct a representation, like a histogram for all of those sample means, that is what is normal. So the central limit theorem is telling us that as long as we collect enough information, and in this case, enough information is defined as a sample size greater than or equal to 30. So information are the observations or the sample size. As long as our sample size is greater than or equal to 30, we can say that the sampling distribution of X bar is approximately normal. And if the sampling distribution of X bar is approximately normal, then we have the ability to do things like make statements about the sampling error, or as we will see in a little bit, conduct inference. On slide 25, I have the central limit theorem written out in its sort of generic expression. So it says, for relatively large sample size, the variable X bar is approximately normally distributed, regardless of the distribution of the variable under consideration. The approximation becomes better with increasing sample size. So the main result here is that as long as we collect enough information, so as long as we collect a big enough sample, we can assume that the sample mean will have a sampling distribution that is approximately normal, no matter, regardless, I should say, of the shape of the population. Okay. Any questions about that idea? Yeah, so the main result, if I had to put it in my own words, the main result of the central limit theorem is that as long as we collect enough information, or we collect a big enough sample, so big enough sample, enough information, this would be the same thing. As long as we have a big enough sample, we can assume that the sample mean will have a normal distribution, regardless of the shape or distribution of the population from which we are sampling. That is the crux of the CLT. No worries. Any other questions? Okay, so this brings us to the conclusion of lecture set 1. Lecture set 1 was meant to be a summary of the most important concepts from Stat 151 in terms of what we are trying to accomplish in the course. So some of the main takeaways from this class are that the sample mean is in fact a random variable. That's what we spent the majority of Wednesday talking about and the last 16 minutes or so talking about. That we can define the distribution of the sample mean. So if we sample from a normal population, X bar is going to be normal. That's the easiest case. But if we sample from a non-normal population, as long as we collect a big enough sample, we can assume that X bar is normal. And big enough sample is typically defined as n greater than or equal to 30. But the truth is that that sample size varies depending on how far away from normality you really are. In some cases, you can get back to normality with 10 observations. In some cases, you need 50 to 100 observations. So this is a rule of thumb. It's not a hard fact, if you will. Finally, X bar is the estimator that we are going to consider most often in this course. So it is the value that we will see or be using or focusing on quite often throughout the first few weeks. In fact, a lot of this course is dedicated to estimates of center, and we will talk about why X bar is reasonable and what to do when X bar is not reasonable around the 7th week of the class or so. All right, so I'm going to switch over to lecture set 2. There's some cumulative exercise given at the end of lecture set 1, so you can work through these. I'll post solutions to these with the completed lecture set. Most lecture sets include some kind of cumulative exercise just as a little bit of extra practice. All right. Okay, so in lecture set 2, we are reviewing hypothesis testing and confidence interval construction for a single population mean. In lecture set 3, we will then review these ideas for 2 population means with some additions. Okay, so in this particular lecture set, we're going to start off by talking about confidence interval construction, and then we're going to talk about hypothesis testing. Those are the 2 main focuses. We're going to talk about these using 2 different distributions, the standard normal distribution and the student t distribution, and when to differentiate between each. We will talk about interpretation of the interval and interpretation of the hypothesis test, and we will also talk about relationships between the 2. So how you can essentially infer the result of one from another. So the point is that the hypothesis test and the confidence interval are very similar, but they have different sort of, you can use, from the interval, you get a very strict interpretation of the parameter or estimate for the parameter. From the hypothesis test, you're more so answering a question about what you think or how you think the parameter behaves. So they have different purposes, but they are very closely related. All right, I mentioned before, I think a bit briefly, that this idea of being normally distributed is a very important concept in the context of statistical inference. So in particular, when we are building a hypothesis test, or we are constructing a confidence interval using the standard normal or the student t distribution, we rely, or we start off by assuming that the population from which we sampled is normal, or that we collected enough observations to assume that X bar is normal. So that is that we collected enough information to let the CLT take over. Formally, the assumptions that we will be focused on in the context of building a confidence interval and constructing a test for a single mean are that we collected a simple random sample. So basically that each observation in the sample is independent from another. And again, that we can assume that the sample values, or rather that the population from which we sampled was normal, or that we collected enough information that the CLT will take over. So these are the two major assumptions that we will have to focus on and validate as we work through these illustrations. Okay, so what is a confidence interval? A confidence interval is simply two numbers that we call the lower bound and the upper bound. The lower bound and the upper bound are estimates of where we believe the true mean is located. So they are, strictly speaking, two numbers that we think mu, the population mean, falls in between. Confidence intervals are constructed using what is called the confidence level. So we can have essentially different amounts of confidence in our constructed interval. And there are trade-offs between being very confident and being less confident in terms of the range of the interval. And this is something that we'll talk about a bit later as well through illustration. Now, one of the big things about confidence interval construction is understanding how to interpret the interval. So a confidence interval in itself may not contain the true mean. So for example, I have a question on slide 3 that asks, true or false, there is a chance that a confidence interval will not contain the true parameter. And this is actually true. Okay. So there is the possibility that we collect a sample from Jennifer, yeah, they're on the on Blackboard. There's a folder that says statistical tables and course content, and then they should be in there. Yeah. Okay, sorry. Right, so when we construct a confidence interval, there is always the chance that the interval is based off of, say, a bad sample. So maybe we collect a sample that isn't representative for some reason, or we get some outlying points that really mess with our estimates. That particular confidence interval for that sample might actually miss the true mean. So we would get out two numbers that don't actually contain the value of mu. This can happen, and it will happen some percentage of the time. But the idea when we are interpreting a confidence interval is that our interpretation is reflecting the idea of repeatedly sampling from the same population. So in the illustration on slide 4, this vertical bar going down the middle here, this will be mu. Okay, so this is our population mean. Each horizontal line is a confidence interval. So this is confidence interval 1. This is confidence interval 2. This is confidence interval 3. This is confidence interval 4. This is confidence interval 5. I'm just kidding. And then it goes all the way down to confidence interval number 20. Okay. So what you can see from this illustration is that confidence intervals 1, 2, 3, and then 5 through 20, they all overlap with mu, which effectively is representing the fact that they contain mu. So mu is inside 19 of the 20 confidence intervals. But confidence interval 4 does not contain the true mean. So each individual interval is either going to contain the mean or it is not going to contain the mean. Okay, so it's a binary problem. 1, you contain it, 0, you do not. So it's yes or no, it will contain the population mean. But across the 20 different samples, you can see that 19 out of the 20 contain the population mean. This is why when we interpret a confidence interval, we never write statements like the probability that that the true mean is between the lower bound and the upper bound is 95%, or we are 95% sure that mu is between this value and this value. When we interpret the individual confidence interval, we use the word confidence to represent this idea of repeated sampling. So the idea that we have collected multiple samples from the same population and some proportion of those samples contains the true mean, or some proportion of the confidence intervals based off those samples contain the true mean. So the generic, one of the generic expressions that we can use is we expect that 95% of the case samples will produce a confidence interval that contains the population mean. And in general here, this percentage level is going to change. So we can actually think of this as being 1 minus what we call alpha. I'll come back to define that in a little bit, but we have a 1 minus alpha % chance of containing the population mean. So 95% is kind of the generic. We'll see more illustrations of this momentarily if you don't quite remember where that value comes from. But the general interpretation for any confidence interval is in terms of repeatedly sampling, which means that we are interpreting in the context that we have collected a lot of information from this population, or that we have collected many samples from the population and we have built an interval for each sample. Okay, so if we construct a 95% interval for the population mean, and we're only using one interval based off of one sample, our typical interpretation of that interval will be something like we are 95% confident that the population mean is between the lower bound and the upper bound. This is the generic interpretation for a CI, the expression that's given at the end of slide 5 here. And again, this is because of that idea of repeated sampling. So the word confident reflects the fact that we know if we collect, say, 100 samples and we build a 95% confidence interval for each sample, that 95 of the 100 should contain the population mean, and then 5 out of the 100 shouldn't. But we don't know which one is and is not going to contain the population mean. All right, so constructing a CI can be done in 3 steps. The first thing that we would do before starting construction is check the assumptions. So the process for building a CI is basically assumption check, 3 steps defined on slide 6. So in step 1, we would state, in step 1, we would compute the confidence level. Most often you will be told the confidence level directly, but there are situations where you could be told what alpha is, which is called the significance level, and I'll define that a bit later. There could be situations where you're given alpha and then you have to compute the confidence level, which is just 1 minus alpha. Then we will find either the z-score or the student t-value that corresponds to our confidence level. We use the z-score when we have the population standard deviation. We use the t-value when we do not have the population standard deviation. So the question on slide 6 says, when do we use z and when do we use t? Basically, we use z alpha over 2 when sigma is known, and we use t alpha over 2 when sigma is unknown. So if we have to estimate the population standard deviation, then we have to, if we have to estimate the population standard deviation, we would use a t-value. So the t-value is actually more common because it essentially is the value you use when you're relying purely on sample estimates. But in some situations, you might know sigma, and in that case, you can use the z-score. Okay, the formulas for the confidence intervals, as you can see on slide 6, are extremely similar. The only difference is the substitution of the t-value compared to the z-value, and then you have sigma here compared to s here. So again, you can see that the t-value goes with s, and that the z-score goes with sigma. Okay, so I usually say s to t, sigma to z, as kind of a rhyming rule, if you will. Doesn't really rhyme though. And then on step 3, we would interpret the interval. And the interpretation is just going to follow that generic expression that was given at the end of slide 5. We're just going to adapt it to reflect the situation that we are working in. So basically just to talk about the variable that we are interested in estimating. So when sigma is known, so the rationale essentially, so why does z go to sigma? Why does s go to t? If the population is normal, or that we can assume that x bar is normal. When the population standard deviation is known, it means that you are properly standardizing x bar. So therefore, you are essentially finding a z-score for x bar. This is the underlying idea. Okay, so we saw an example of this last class, but so standardization is when you convert a value into a unitless number on the 0-1 scale. So if x normal, then z is standard normal. Okay, so this is the definition of standardization. So the formula for standardizing any value is the value minus its mean over its standard deviation. So z is equal to x minus mu over sigma. If x is normal, then z is now standard normal. We learned that x bar has mean mu subscript x bar equal to mu and has standard deviation sigma x bar is equal to sigma over the square root of n. So therefore, if you were to standardize x bar, you would subtract mu and divide by sigma over the square root of n. Okay, so z is equal to x bar minus mu x bar over sigma x bar, which is x bar minus mu over sigma divided by the square root of n. If sigma is known, you have a proper standardization. So therefore, if x bar is normal, then you have a z-score. And that's the rationale for why we use a z-score when sigma is known, because you're basically performing a proper standardization of the random variable x bar. Okay. Now, if sigma is unknown, what we do is we simply replace sigma with little s, which is the sample standard deviation. The result of this is that when you standardize, you no longer have a z-score, but you have what is called a student's t random variable. And the student's t random variable, so what you're actually doing is called studentizing, okay? So this, again, is basically the rationale or part of the explanation for why we associate z with sigma and why we associate the t value with the sample standard deviation, because of what happens when you standardize x bar using sigma versus s. Okay. So here is a simple illustration of how to construct a confidence interval. So first off, we have the following SRS from a normally distributed population with mean mu and sigma is equal to 20 is given below. Okay, so our assumptions here were that we collected a simple random sample and that the population from which we sample is normal, or that we collected enough observations for the CLT to take over. So we want to construct a 95% confidence interval for the population mean. Sigma is given to us in the question description, so we can use an interval based off of the Z-score. From the description of the problem, we are told that we collected a simple random sample. Okay, so we can say, if we were to just sort of summarize the assumptions, we would have SRS, and this would be good. And then we would have normality, and that would also be good. So we have an SRS because we're told that we have an SRS, and we have a normally distributed population because we are told that we have a normally distributed population. So we can check off those two assumptions. We are told that we are asked to construct a 95% CI. So what we are asked for here is to find a Z-score that has alpha over 2 of the area in the upper tail of the curve. So basically, on step 1, the confidence level is given, which is 0.95. What we want to do is find the Z-score to plug into our confidence interval. So this is going to be a Z-score with 0.025 of the area under the curve in its upper tail. This is what the nomenclature is telling us here. Okay, so this part here is saying here is a normal distribution. It's centered at 0. We have Z 0.025 here. Okay, so this red shaded part here is a size 0.025. So we have 0.025 of the area under the curve in the upper tail. So if we were to go to the Z table now, okay, if we have 0.025 of the area in the upper tail, that would mean that we have 0.975 of the area under the curve to the left of our Z-score of interest. So the total area under the curve is equal to 1. We have 0.975 to the left, 0.025 to the right. So if we go to our standard normal table, which is a cumulative table, so it starts at -infinity and works its way up to the Z-score. So this visualization here is showing us that all of the areas inside are cumulative areas or percentiles. Then if we can find 0.975 in this table, which is right here, then we can come out to the axes to find 1.96, which is the Z-score that we are using for this particular confidence interval. Right. So that's why here we have Z subscript 0.025 is equal to 1.96. Now, I assume that some of you haven't seen this kind of thing in a while, so I'm going to go over another example of finding this when we build a confidence interval from scratch. But these are, again, just drawing back on working with the standard normal curve. So if you're not sure about how this is being done exactly, you just need to review working with standard normal random variables. And there will be tons of examples that you can use for this. I can give you some too if you need some practice. Once we have our z-score, we're just plugging into the equation. So x bar plus or minus z subscript 0.025 times sigma over the square root of n. Then we're plugging in x bar, which is 108.3. And then when we plug in for z alpha over 2, sigma and the square root of n, we end up with 12.396, which is what we call the margin of error. This gives us the confidence interval 95.904 to 120.696. And then we can say for this normally distributed population, we can be 95% confident that mu is between 95.904 and 120.696. All right, so let's look at another illustration of building a confidence interval now. Okay, so we have a simple random sample of 678 females that believe on average 3.22 children is the ideal number for any family. Compute a 90% confidence interval for mu given sigma is equal to 2. Okay, so let's start off by writing down a quick assumption check. So we have two assumptions: that a simple random sample was collected, and that we can assume that the population was normal, or we collect enough information that the central limit theorem will take over, and we can assume that x bar is normal. So the simple random sample assumption is valid because we are told in the question that we have a simple random sample of 678 females. Now, normality is also valid. So we can check this off. And we can say, since n is greater than 30, the central limit theorem, well, let's say that this is true by CLT since n is greater than 30. So we are using the central limit theorem to make the assumption that the sample mean x bar is normally distributed. Okay, so this is a way that we can validate an assumption, if you will. Okay, now we want to construct a confidence interval. So on step 1, we will have 1 minus alpha is equal to 0.90. So we want a 90% CI, which means 1 minus alpha is equal to 0.9 by definition. So that means that alpha is equal to 0.1. Since sigma is known, we use z alpha over 2. So we will have, here, I'll just move this over. Sorry, one sec. Spacing. Okay, so since sigma is known, we can use z alpha over 2. So we're using a z-score because we have sigma. All right, so z alpha over 2 is equal to z 0.10 over 2, which is z 0.05. If we sketch the curve, so this is our standard normal curve. We have 0 here, and we have z 0.05. So that means that this is going to be a size 0.05, and that the remaining part or the remaining area under the curve will be a size of 0.95. So what we would do now is we would go to our standard normal table. We would look up 0.95, which is one of the special cases of the standard normal curve. You can see that 0.95 is actually directly in the middle of 0.9495 and 0.9505. Typically, we just round to the closest value, but in this case, and this is only one of two cases, we can actually just take the average because 0.95 lies directly in the middle of those two numbers. And we end up with the average of 1.64 and 1.65. So that gives us 1.645. So we have 1.645. All right. So now on step 2, we're going to have x bar plus or minus z 0.05 multiplied by sigma over the square root of n. So this will be 3.22 plus or minus 1.645 multiplied by 2 divided by the square root of 678. This will be 3.22 plus or minus sorry, didn't write this one down. Okay, plus or minus 0.12635. So this will give us roughly 3.094 to 3.346 as our confidence interval. So I'm subtracting and adding to the mean. Now, our third step here is to interpret. This is the same thing as what part B is asking us. So I'll just make a note here that part B is step 3. Those are the same thing. So now we can say we are 90% confident that the true mean number of children that this population of women thinks is ideal is between 3.094 and 3.346. Right, so that would be the explanation or the interpretation of that interval. Okay, so that's the first illustration of constructing a confidence interval for one population mean. Again, in doing this, we are reviewing working with the standard normal distribution. If sigma is unknown, we would then use the student's t distribution. So we will review working with the student's t distribution in the same sort of way that we reviewed working with the standard normal distribution. The biggest difference between them, aside from working with a different table, is just that you substitute the z-score for the t value and you substitute sigma for s. So on assignment 1, the question 9A or 8A now, I think it is, that asks you to construct the interval. In that situation, you're using a student t interval because you don't have sigma. So the process is going to be very similar to what we saw here, but we'll review an example of that on Wednesday so that you have an illustration of how it works. Otherwise, everything is pretty much the same in terms of interpretation, assumption check, and finding the confidence level. Okay, so I'll stop there for today. On Wednesday, we'll continue to work through this example, and then we'll look at some student T examples as well. And then by Friday, I think we should be on to hypothesis testing. But again, that won't be on the first assignment. That would probably be on the second assignment. Yeah, the confidence interval is an interpretation for the population mean in this case. So this is meant to be meant to give us an estimate of the population mean. Okay, cool. Okay, so yeah, have a good couple days, and I will talk to you guys on Wednesday afternoon. And as always, if you have any questions, let me know.